It's very difficult to understand the concepts in this chapters, so we will concentrate on addressing modes and the clocks. Let me begin by pointing out some errors in the book that there is no absolute addressing mode. It's really direct addressing mode, and there is no implied addressing mode. It should be inherent addressing mode. In the immediate addressing mode, we take a piece of data, in this case 3F in hexadecimal, and we load it directly to the accumulator, remembering that everything takes place in the accumulators. LDAA is the opcode, which means load accumulator A, and then 3F is the hexadecimal operand. The pound sign indicates the immediate addressing mode. The dollar sign indicates hexadecimal. If the opcode has no pound sign, then we are in the direct addressing mode. In the direct addressing mode, the microprocessor will go looking for a memory location, and then whatever is in that memory location will be loaded into accumulator A. In this example, the microprocessor will go to memory location 0150, and whatever is there will go into accumulator A. But we don't know what's in memory location 0150. So in this case, I just put a question mark, and we say that whatever is there will go into accumulator A. In the inherent addressing mode, we have opcode but no operand. In this example, we have two accumulators, A and B, and we want to clear them, which means that we're going to overwrite whatever exists in the two accumulators with 0. With the index addressing mode, we first use the index register, and remember the index registers are used for counting. First, we load index register X immediately with the hexadecimal number 1000. Next, we take the index register and add hexadecimal number 20, with the result is that the index register now is loaded with 1020. 20 is called the offset, and X is the index, and the two things are added together. And there is another index register Y, and it works in the same manner. Once we load the index register, then we execute the next line of code, which is load accumulator A. But in this case, the microprocessor will go looking for a memory location, which is 1020. Whatever is contained at memory location 1020 is then loaded into accumulator A. The relative addressing mode is used because we need to jump backwards and forward during the execution of a program. Supposing we have a little program and notice that we start at 0120 and notice that the program counter is keeping track of each line of code. The microprocessor begins executing the program, but we decide that when we get to memory location 0135, we're going to execute the jump command and we want to jump backwards to 0120. So we have to add a number at memory location 0136, which will cause the microprocessor to jump backwards to 0120. If we subtract 0136 minus 0120, we find that we need to jump backwards 1/6 number of steps. In order to execute the jump backwards, we need to convert 1/6 to a negative number in hexadecimal. We begin the conversion by taking the hexadecimal number 1/6 and expressing that as a binary number but in 16 bits. Next, we take the binary number and take the ones complement, which simply means to complement each and every digit. We now take the ones complement and we add a 1 to it, and this is called the twos complement. Notice that now the most significant bit is a 1. If the most significant bit is a 1, we agree that this is a negative number. Finally, we take the binary number, which we know it to be a negative, and convert that back to hexadecimal, and the result is FFEA. If we take our hexadecimal number and put it at memory location 0136, then that number will get added to 0136, and the result is the microprocessor will jump back to 0120. The speed of the microprocessor is determined by the crystal which is contained on the circuit board. In this case, the crystal is running at 8 megahertz, but there is a circuit that divides by 4, so the system clock or the E clock is running at 2 megahertz. If the frequency is 2 megahertz, then the period is 1 over 2 megahertz, which is 500 nanoseconds. There are actually two clocks that are running at the same time executing opcode, the E clock and the phase 2 clock. The E clock you can see on an oscilloscope, but the phase 2 clock you cannot.